A lot of you have a good sense of this now. So with this one, now that I've got the reactions up there, you can look at how to form the two groups. Of course, here's the aniline, the amino group there. So that's going to come from a nitro group, the reduction of a nitro group. And then your alkyl group, remember, is connected at the primary position, which means you have to use this type of a process, not this. Whoops, not this. Because of the potential for a carbocation shift with the alkyl version of that. If you're unclear on that, always err to this side, because that's always going to be better. All right, so the question, whoops. So then these are the two routes you're going to take at some point. The question becomes then, unlike a traditional synthesis problem, what order do you do this in to make sure that you get the appropriate product? And I don't have space too much here. What you want to do is, it doesn't actually matter which group you put on first, but the trick is that you have to make sure to have a meta director for the other one. All right, like these two groups as they are right now are ortho-para directors. They both are. So having either one of those groups on the ring, you're going to get the wrong substitution. So what you need to do is put the second thing on when you're at this middle stage, because both of these things are meta-directors, before you reduce them to the ortho-para director. So one way you might do this would be to nitrate this. Right. And then to use the acyl chloride, although this is a less great way to do it because the nitro group is a stronger deactivator. So it's going to take a little bit harsher conditions to do the Friedel-Crafts chemistry after the nitro group. But from a paper chemistry standpoint, that's fine. Okay, so you want to make sure both of these things are on before you do any reductions, because those reductions end up turning meta-directors into ortho-para directors. Now both things are on there. It doesn't matter which one we do when. We need to reduce. You may be able to even do this all in one step. I'm not sure if that's actually. That actually works. Let me.
Is it all the same step? The one just requires the heat, then should you start it without the heat and just?
Yeah, potentially. Yeah. Let's see what the book says about that. Again, that's kind of that's an experimental thing that you kind of have to try and figure out. Yeah, they do say that this reduction can be done in one step. So. Whether you actually write it in one step or not, I don't really care. But that's how you go about that sort of problem, okay? All right, let's try another one. Now with these synthesis problems, you often run into a problem, and I think we'll see it here. So synthesize this from benzene. Where you want an ortho or a para product as your synthesis product, but since you have an ortho-para director, of course, you get a mixture. Right? Now, in those cases, when we talk about synthesis, that's okay. You can't always only get the one you want. Sometimes you get some byproduct also. We can purify those away. So if you want like an ortho product like this, yeah, it's likely you're going to get some para product there also, maybe even more para product. But we can, for the purposes of doing these problems, we'll assume that we can purify those away. Not worry about them too much. Fun. All right, so let's talk about this one. You got two alkyl groups. There are various ways to do this. There's one much better way than all of the other ways. Okay. Alkyl groups are ortho-para directors, of course, and so you can put one of these on and then put the other one on and so on. And that would mostly work. You get some decent yield and you could purify out the other product. There's one way to do this where you get very good, probably best yield, okay? And that is by using the blocking group chemistry that we talked about before. Okay, so first, what kind of chemistry are you going to use to put each of these things on here? Like this big group, what do you need to use to do that? Right, that's the Friedel-Crafts Clemenson chemistry here over on the right. You can't use this typical alkylation because of the carbocation shifting possibility. So you go from the carbonyl. And do something like this. Okay, now, as an aside to that, same thing with the previous question. How do we know the order? How do we know which one goes where? Well, it's not necessary to magically come up with this thing in your head before you write anything down. Just start writing these reactions down and then ask yourself, well, would this actually work this way, or do I have to do it in a different order? There's no need to come up with the whole plan in your head and try to work it all out before you go through it. Just write some stuff down. Okay, here's how we would do this part, for instance. We would take this, followed by that reduction. Yeah, I was just saying you could make this way, right? And then the methyl, we would use the other chemistry because we don't need to. All right, now, the problem with doing this one first, as I've written it here, is that if we then go to add the methyl, we have the big problem that this product is probably a pretty minor product because of the size of this group. This is a big, bulky group, and so the major product is probably going to be the para product, which we don't really want. So there's two solutions, one better than the other. One solution is, well, maybe add the methyl group first, right? Because then you would expect some more ortho substitution than para. And that's fine. That's a reasonable way to do it. But there's a better way to do it, and that is to use the sulfonic acid blocking groups. So if we put a sulfonic acid on here, or a sulfonate group, now we've used that para preference to actually block the para position and help direct to the ortho position through the meta-directing of the sulfonic acid. So then when we go add the methyl groups, the methyl group, we expect that that's really the only product we get. It's really the only possible product at that point. So in that way, we can very carefully select for that product. Okay. Then we need to remove that blocking group. in dilute acid, and we have our product in good yield. All right, so that's the best solution to that problem. All right, we can also do this. We can also use bulky groups to our advantage in other interesting ways. So let's say we want to do this kind of a thing. Okay, so your first thought, you're going through this, okay, I gotta put this on, I gotta put this on, fine, can do all those things. We know that this can be formed from reduction of some Friedel-Crafts chemistry, and we could put that on first, then put the methyl group. Those are all fine. But what if we wanted to do this in very good yield with the minimum amount of ortho product? Both of these things are ortho para directors. So we expect, and they're both pretty small, really. So we expect a pretty substantial amount of ortho product if we tried to add while one of those is on the ring. Well, how do we get around that? Well, what if we add something very big and then get rid of it? All right. So what if we add let's see, how do I do this? Actually, that's not going to work the way I've drawn this. Let's see how I can get out of this. Yeah, we need some further chemistry. We'll talk about this later. Remember this? We need a couple more reactions. We'll get back to that. Sorry, I got lost. Okay. Let's go on to some other stuff. We'll get back to that. All right, so now we've talked about all those electrophilic aromatic substitution reactions. Now let's talk about nucleophilic This is still chapter 19, yeah. Through 19, yeah. So now instead of SEAR, right, we have SNAR, nucleophilic substitution. And so now we're talking about nucleophiles substituting on benzene. So all the effects are reversed because the benzene is now the electrophile instead of the nucleophile. And the thing coming in, the thing being attached, is the nucleophile instead of the electrophile. So we see reactions like this. One of the main important reasons for nucleophilic aromatic substitution, or uses for it as a synthetic technique, is the preparation of phenols. Notice that we haven't yet talked about how to make phenol or phenol. And one way that you can make it is through nucleophilic aromatic substitution, where it substitutes for a leaving group like a bromine. Now, this is a much less general reaction than all the ones we've talked about before. It only works under very specific conditions. And I tell you that sort of as a warning, because everybody likes to do these in their syntheses, and they only work under these special conditions. So we're going to specify those now. So for this to work, and we'll talk about why also. Okay, number one, main one that is easy to forget. You need a powerful electron withdrawing group. Like a nitro, typically. A regular old benzene is not going to substitute readily in this way. So you need to have this electron withdrawing group on there. Okay. Second, this is probably obvious, but you need a good leaving group. Typically bromine or iodine or something, a halide. And third, the leaving group must be ortho or para to the electron withdrawing group. So let's talk about why that is. So the first two, I think we can just describe in general terms. You need a powerful electron withdrawing group because you need to make the aromatic ring, which is usually a nucleophile, into an electrophile. So you need to deactivate it enough, get those electrons out of there, so that it's attractive for a nucleophile to attack it. So that's the first one. Second one, okay, it's substitution. You need a good leaving group for nucleophilic substitution, just like before. The third one, we have to look at at the mechanism to explain and look at some resonance. So let's check out the mechanism. Now, first of all, the mechanism is not the same as nucleophilic aliphatic substitution, which is the old nucleophilic substitution, SN1, SN2. The reason for that is, first of all, you can't actually get something in the benzene ring. Remember the geometry of a regular old substitution SN2 reaction? The nucleophile has to come from the back directly behind the leaving group. Well, in an aromatic ring that's flat, that means the nucleophile would actually have to go inside the ring and go through that way. And nucleophiles aren't small enough to actually fit in there. So that's not going to happen. So it's a different mechanism, and it looks like this. We're going to draw out this because it's important to the resonance here. So here's our para-bromonitrobenzene. And let's say our nucleophile is hydroxide, commonly used in these reactions. The first step is actually for the nucleophile to attack the benzene ring at the position of the leaving group. And in doing so, these electrons are going to move over to the carbon next door and create a carbanion. So we have now bromine here and OH. And this is the intermediate here. Now the reason that this is a stabilized intermediate is because of the position of that nitro group. Because of the position of that nitro group, we can draw a resonance that delocalizes that negative charge to the oxygen. That only works when the nitro group is in the ortho or para position. If it's in the meta position, you can't move the electrons around in such a way to actually get them over to the nitro group. So that's the reason for rule number 3. You have to be able to do this. This stabilized anion is known as a Meisenheimer complex, but it's just another way of saying that the carbanion is stabilized through moving it up through resonance with the oxygen. So then, in the final step, you have the electrons coming back down and kicking off the leaving group. So you regain aromaticity, the leaving group leaves, and you've got your product. Now there's actually another step here that we haven't really talked about, but because we're doing this in sodium hydroxide, you'd actually end up deprotonating this, right? Because this is acidic a little bit. That's why I listed a second step as a workup with acid. After the first step, you'd actually have O- up there. It's just an acid-based consideration. All right, one other thing you might notice from this mechanism is that you need a pretty big difference between what you're putting in as a nucleophile and what's leaving as the leaving group. Because in this final step, when you're losing the leaving group, you could imagine that either one of those things could leave, right? So the thing you want has to be a much worse leaving group than the thing you want to get rid of. Like you see here. OH is not a particularly good leaving group, so that's going to stay on. Bromide is a decent leaving group, that's going to leave. This reaction doesn't work so well with things like bromide versus chloride, where they're both pretty decent leaving groups, and so you might lose either one. It works best when you have a pretty good difference there. All right. So any questions about that so far, about that mechanism or that reaction? Okay. Those 3 rules are key to getting this to happen. Now there's a similar reaction that we'll also talk about here called elimination addition. I guess it's not really its own reaction, it's a combination of 2. When you don't have that electron withdrawing group, you can still do something that kind of looks like substitution, but it's actually not. So if you heat chlorobenzene up with similar conditions, but actually you need really high temperatures now. You can get what looks like a substitution. And you can do this with other types of strong bases too. But some weird things start to happen because it's not exactly substitution. So let's say we look at parachlorotoluene. And instead of sodium hydroxide, we're going to use sodium amide, which is a strong base, in liquid ammonia followed by water. So you expect, okay, we have this pretty strong base, we have this leaving group. It's a non-activated ring, but actually we do get the product. The problem is that's not the only product. You get about a 50-50 mix of these two products. So that's a problem. We don't like reactions where you get a 50-50 mix of two different regioisomers because then you have to separate them at the end. So what's going on here? Well, this looks like a nucleophilic substitution, but in fact it's a different reaction. What's happening is we're doing elimination, getting rid of the leaving group, and then actually an addition. And it's a very strange type of elimination. Here's what's going on. That strong base, amide, NH2 minus, is actually deprotonating benzene. And then, something even weirder is happening. We're doing an elimination leading to a triple bond in benzene. And this is known as benzine.
Isolated?
No. Well, not really.
Because it must be really unstable.
It's really unstable. You can trap it, and we're going to talk about how you can trap it. But yeah, you can't just kind of have a bottle of this stuff. It's an unusual triple bond. The other thing that's strange about it is it's not a true triple bond in that it's not two sets of p orbitals that are bonding. It's actually one of the bonds comes from regular pi bond. The other bond comes from a pi bond between sp2 orbitals because there can't be another p orbital in there. So that's how you can still actually get this geometry. It's an unusual, unique type of triple bond that we don't see in the straight chains. So what happens at this step then is that the ammonia can actually add here, or the amide base can add to the benzine. And it can go to either side. So actually, if you don't mind, let's label this so with a methyl group there so we can see both possibilities. Here's where we get the mix of products. Because the ammonia could just as easily add to the other side of the triple bond as well. Or the amide could add to the other side. If we then work it up with the acid to protonate that carbon, that's what we end up with, what we drew before. So in situations where you have a strong base and you don't fit those conditions from the nucleophilic substitution, you could be likely to undergo elimination addition. From a synthetic standpoint, that's fine for a very simple, like a benzene ring or something. That's not so fine when you start getting other types of substituents, because now you're going to have mixtures of products. So it's usually something to be avoided, but something that can happen. Now, how do we know about benzine? Well, what you can do is in this reaction, you can actually put in a Diels-Alder-diene, and you can trap it. So you can take benzine and use it in a Diels-Alder reaction. And you end up with something like this. And this thing is a regular stable molecule that can be isolated. So the existence of that proves that it was a benzine intermediate. And that's how we know, even though the benzine itself isn't isolated, that's how we know it was there. Because we isolate this other thing. All right. So let's look at some problems with respect to this. We do a lot of synthesis problems. Let's do a mechanism problem. This one's from your book. Oops. All right, so draw the product and mechanism of this reaction. So let's look at this. First step, as before, well, we're gonna check those considerations first. Do we have a strong withdrawing group on the ring? Yeah, we've got the nitro group. Do we have a leaving group? Yeah, we've got chloride. And are they in an ortho or para arrangement? They are. Yes.
I have a good question. You drew the double bonds differently in the bottom structure.
Oh, yeah.
Could you drew them back the same
The
way?
same? Okay.
Because it's confusing.
Okay. But you know it's the same, right?
Yeah.
I mean, you can always draw either resonance structure whenever you want.
Right.
Okay. All right. So let's talk about now how. So we've settled then on the substitution mechanism rather than the elimination addition mechanism. So then we draw it. You've got the nucleophile attacking, and then ordinarily we would just draw that, or we could just draw that the carbanion forms next to there. But what we really know is happening is that the whole reason that this can form is because of the nitro group pulling those electrons away. So a better way to do this is to actually draw the resonance going all the way back to that oxygen. Whether you want to do that in one step or you want to draw the one and then the other step in the resonance, whatever. But this is really the more important resonance contributor to the intermediate. And then the second step is losing the leaving group and becoming aromatic again. And if you really want to be super exact about everything, you leave this as an O minus and then protonate it in the next step. But the book doesn't emphasize that. I won't worry about it either. The important part are these mechanisms. What I will worry about is if I give you something like this on the exam and you draw kind of a typical substitution mechanism. You know, nucleophile comes in, leaving group leaves. That's incorrect. That's not what's happening. You have to draw this as a two-step process where the nucleophile attacks, followed by the leaving group leaving. And if it's an addition or elimination addition, then there's that mechanism as well. Okay. Questions about substitution, elimination, addition? Okay. That completes chapter 19. Let's...
So the whole next week is review?
No, we'll go on.
Yeah.